Hello, friends. Welcome to what would have been our final class of the semester, Tuesday, May 5th. It's been an odd end of the semester. I hope you have been holding up well and that you and your family are safe and healthy. Mine are continuing to be, so thank you for your thoughts and worries. We haven't done nearly enough astronomy pictures of the day this semester. I apologize for that. I'm going to give you a couple of them right now. Here we go. So today's astronomy picture of the day, I'm filming this on Monday, May 4th, is a time-lapse, well, it's actually a series of images taken by the Bepi-Colombo space probe. Bepi-Colombo we'll talk about in a minute, but it is it's on its way to Mercury, and it has to fly by Earth to get there. And we'll see why that is in a second. But this is a series of images that was taken by Bepi-Colombo as it was flying by Earth. It's only 5 seconds long, but this is what it might look like to fly, at least approach the planet Earth. Let's try that again. In the foreground, you have the space probe itself, and Earth, of course, approaching. So that's fun. What it would look like if you were to approach Earth from space. It's hard to get to Mercury. This isn't obviously a solar system class, but let's just take a minute and talk about how hard it is to get to Mercury and why we haven't done it but more than a few times. So the problem is not getting to Mercury. The problem is staying at Mercury. So let's look at this is the Wikipedia page for Bepi-Colombo. And there's, of course, you can read all about it, but I want to talk about how to get there. This is pretty amazing. This is again, if you think about Kepler's laws, let's just look at the inner part of the solar system. I can't really pause this, but you can see the Earth and Venus and Mercury's orbits. The Earth is in blue, dark blue. Venus is in light blue. Mercury's in light green. We are these look much more elliptical than they really are. We're looking at it at kind of an angle, which makes it look a little more squished down. But so let's say you wanted to go to Mercury, right? You might think you would just launch this thing straight down, but it's not going to stop at Mercury, right? The hard part is not getting to Mercury. The hard part is stopping at Mercury. And to do that, you really have to slow yourself down a lot. And the way you do that is you make these flybys of planets. You can do planetary flybys in one of two ways. You can either do it on the forward edge, which will slow you down a little bit, or on the backwards edge, which will speed you up. And so in order to get this space probe not only down to Mercury's orbit, but to stay in Mercury's orbit, it requires, in this case, something like 9 or 10 or even more flybys. So let's watch this probe. It's going to be going around, does a first flyby right there. You can see how it slowed down. So Venus, a couple of Venus flybys. Each time it does one of those flybys, it enters a lower orbit. You're robbing some orbital energy, and it enters a lower orbit. And now it's going to do several orbits in Mercury orbit-ish before it finally settles in. That's why it's really, so this is a pretty amazing task, right? You're launching a projectile from the Earth, and you're basically bouncing it off of moving objects 11 different times before it finally gets to its target. It's a pretty amazing accomplishment, and they don't call it rocket science for nothing. This is, again, from the first approach, how, from a Mercury-centric view, this orbit actually goes. And how it actually gets back and finally reaches Mercury at basically 0 velocity. That's how you get to Mercury and stay there. It's very complicated. So that's a little aside on Bepi-Colombo. I'm going to show you one more astronomy picture of the day. I'll show you, this isn't the one. This is a message from Earth. This is what we sent out on Voyager. If aliens, this is our message to aliens. includes lots of interesting encoded things. You can read about it if you want to. There's a thing about radio astronomy. There's a nice galaxy thing, but this is the one I want to talk about. This is an image we've looked at many times this semester, actually. This is the Andromeda galaxy, the closest very large spiral galaxy to us, with its two elliptical galaxies, satellite galaxies. And this is the caption is all about the Shapley-Curtis debate of 1920 on island universes, and the debate about what these things were and how that was not solved until that Hubble went in and found Cepheid variables in M31, which is a topic we talked about in class already. The cool thing about this, obviously, it's a nice image of Andromeda. I want to click on this link and show you this previous astronomy picture of the day from April, from earlier this year. This is very cool. This is an observation that was taken of the Andromeda galaxy in 1923. This is Hubble's discovery plate, where he discovered that there were variable stars in Andromeda. So this is, again, there's no color images, there's no digital images. At the time, these were taken on glass plates, right? So you go to the telescope, and you had access to one of the biggest telescopes in the world. You point the telescope at your object, you put the glass plate on the focal plane, you let the exposure develop, integrate, let it expose to light. You take that plate to a dark room and you develop it, and you end up with something like this. This is the Andromeda galaxy. It's a much less refined in terms of contrast image than you're used to seeing of the Andromeda galaxy, but this is the best that could be done in 1923. And this thing up here, you see, Edwin Hubble himself has written in VAR exclamation point, which means he's found a variable star. He's very excited. Which one is it? It's that star right there. That's the Cepheid variable that Edwin Hubble used to determine the distance to the Andromeda galaxy. In case you thought it was some prominent thing, how did he know it was a variable star? Well, he must have had other plates that he was looking at and noticed that the brightness of that particular star was different in the various plates. And so again, if you remember, by measuring the period of variation of that particular star, he was able to determine the luminosity. And from the luminosity, you can determine the distance. And he discovered that the Andromeda galaxy must be much further away than anything that had ever been measured before, and therefore must be, in fact, a galaxy of its own, which solved the whole Shapley debate itself. Okay, that I thought was very cool, and you guys needed to see it. Okay, let's get to today's topics. Let me stop sharing that. Today's topics are the biggest questions we can answer. Where did the universe begin, and how will it end? Doesn't get any bigger than that. Okay. Stick with me. Okay, here we go. Today's review question. What is the shape of the universe if omega is greater than 1? I'll let you commit to an answer. So omega, remember, is the mass density of the universe. And omega is defined such that omega equals 1 is a critical universe. If we have omega equals 1, we have a flat universe. I really mean omega total here if you add up the dark matter and the normal matter and the dark energy. If it adds to exactly 1, we have a flat geometry. If it's less than 1, we have an open geometry. If it's greater than 1 in this particular case, we have a closed geometry, which corresponds to a sphere if you were to take a 2-dimensional universe and think about it as curved in the 3rd dimension. So that's that. So this is the question we begin this class, the last class, with, can we look back to the beginning of the universe? And that is, the answer to that question is yes. If the universe has a beginning, and that beginning was some finite time ago, we should be able to look back to the beginning of the universe. How? Well, remember, the further back in space we look, the further back in time we look. We don't see the sun as it is now. We see it as it was 8 minutes ago. We don't see the Andromeda galaxy as it is now. We see it as it was 2 million years ago. We don't see distant galaxies as they are now. We see them as they were however long it took that light to get to us. So the further back, further away from us we look, the further back in time we look. So we should be able to see directly what the beginning of the universe was like. That's cool. What would we see? What would it be like? If we were having this class in class, I would pose the question to you and we would have some conversation and there would be some nice back and forth, and I'm missing all of you being in front of me to ask you this question, so I'll just have to answer it myself. What was it like? Well, let's think about how these things work. We know that if you, the universe is expanding, but if you run the clock backwards, it was compressed, right? What happens to a substance, a system, if you compress it? What happens to its temperature? What happens to its pressure? It turns out all of those variables, as you take a same volume of stuff, same amount of stuff and compress it into a smaller volume, have to go up. The pressure has to go up. The temperature has to go up. Lots of these interesting variables, thermodynamic variables, have to go up. So we expect, if the Big Bang Theory is true, that the universe at the beginning must have been much hotter than it is today. So we should be able to see that. Now, this is an interesting story. The Big Bang Theory was not that terribly old, and as these things go, and it was not universally accepted by astronomers at the beginning. In fact, the term Big Bang was used by astronomers in the 30s and 40s and 50s as a way to ridicule it, to make it, what do you expect? The universe started in some Big Bang? Well, the name stuck, and yeah, we really do think that. But this is an important topic for science itself, because science evolves. As new evidence comes to light, theories update themselves, paradigms change. It doesn't happen very often, but this is one of those paradigm changing moments. And rightfully so, scientists are skeptical of paradigm changing evidence, right? They really have to be convinced, because it's a lot. The paradigm was there for a reason. The paradigm before Hubble discovered that the universe was expanding was that the universe was infinite in extent and infinite in age, and that it had always been look about the same the way it did now, and it would always look about the same as it did now. And so astronomers and scientists and physicists at the time were very loath to abandon that idea of a universe. And in fact, they tried lots of crazy things to save that paradigm, that infinite universe, even given what was new evidence of the expansion of the universe. So how, you might ask, can you have an infinite universe if it's expanding? Well, one model that was given a lot of serious thought and brain power to was the steady state model of the universe, right? So in the normal Big Bang model, you have an evolution of the universe that looks like this. You have the same amount of matter. As the universe expands, it's just spread over a larger and larger area, and the density of stuff goes up over time. You extrapolate this one backwards, you get to a Big Bang where all these galaxies are in the same place, and a hot, dense early part of the universe. The density of matter here will decrease over time. In the steady state theory, the idea is that yes, okay, we concede your point that the universe is expanding, but that doesn't mean necessarily that it had to have a beginning. What if, as the universe expands, new matter pops up and makes new galaxies, and new galaxies pop up to fill in the holes that were left as the previous galaxies separated away from one another. That way, if you move forward in time, the density of matter is fairly constant over time. And if you extrapolate backwards, you can do it forever. And if you extrapolate forward, you can do it forever. And the universe is expanding, but always looks the same at all times, roughly. And so, great. How do we tell the difference between these? Both of these are, I mean, you might argue, how is it that you're making matter out of nothing? And that was a serious problem with this theory. But let's try to think of a different way that we could resolve the conflict between these two different theories of the universe. How is it that we could tell the difference? Well, one predicts a very hot, dense universe, beginning of the universe, and one does not. One predicts a universe that is infinitely old and never had a hot, dense phase. Well, okay, that's the question I'm asking you. How can we tell the difference between these two? Well, that is exactly right. If we can look back in time and see evidence of a remnant period of the universe's past where the universe was hot and dense, then we can prove that the universe had some hot, dense state, and that will eliminate the steady state and strongly support a Big Bang model of the universe. Okay, so I'll stop this particular video here. We'll come back in the next one and talk about what the predictions actually, what the models actually predict, and whether we can see such a thing.